Hello everyone, my name is Jesus Pateño. I studied computer science in Universidad Autónoma de Guadalajara. Today I will present you my thesis project named Development of a Traffic Sign Dataset at ZMG and its evaluation using deep learning algorithms. My project was Gilberto Ochoa and Juan Antonio Vega. So what do we see in here? Where we can see a train, a ladder, a building with windows, it is nothing more than ones and zeros from any machine perspective. This data is arranged in certain format that can be translated into what we consider to be illustrations. All this matter is at the end the basis of computer vision. But what is computer vision? This topic has been around for the last 50 years and it started when visual information is captured by sensors, and after understanding this data, interpretations are made. In our case, for humans, eyes act as our sensors and our brain as a processing unit. On the other hand, in computer vision, cameras capture the information and CPUs does the processing. Ideally, both human and machine will come up with the same interpretations. From an image, we can extract two types of information. Geometric information, which collects data related to the shape and position of the object. On the other type of data that can be collected is semantic information, which is related to the classification of the object into different classes or categories. Four of the main challenges in computer vision are image classification, object localization, semantic segmentation, and object segmentation. These challenges have their own similarities and difference, as well as their own difficulty degree. In the case of our project, we will decide to tackle the problem of object localization and classification. For these particular challenges, there has been plenty of different approaches, each of them getting better results than the previous one. It started from the long time ago with handcrafted matrix to more recent and complex methods. However, something that should definitely highlight is this breakthrough that occurred in 2012 when AlexNet in ImageNet Challenge uh, obtained the best results from that time and changed completely the future on this matter. Since AlexNet was using a deep learning algorithm, one with a 15% points away from the second contender, these kind of techniques became quite popular. The second place did not use deep learning for this challenge. Ever since this breakthrough, the winners from this challenge were deep learning algorithms that use more and more layers than the AlexNet model. They all get better accuracy as well. As we can see on the graphs, after AlexNet, uh, they came up different models with 8 layers, with 19 layers, 22 layers, one model with 152 layers, and so the one the one with the most layers was ResNet in 2015, and the most accurate one was ResNet and HT with an error rate of 3%. But is that all? Deep learning will solve everything and that's it? Well, certainly it will not. It is only through the combination of a powerful algorithm and a well-developed big dataset that we can obtain these kind of results. There are common object datasets along with their own benchmark that measure every algorithm equally. For instance, we have ImageNet. This dataset with 1,000 different classes and over 150,000 images is publicly available. Also, we have Pascal that has 20 different classes and 11,000 images. And finally, there's Coco with 80 different classes and 330,000 images. It is only through this combination that deep learning is a great solution. But what is the problem? Deep learning algorithms are outperforming previous artificial intelligence in image detection and classification. However, there is no trained system capable of detecting and classifying Mexican traffic signs. The metropolitan zone of Guadalajara is an untested area for these algorithms and don't have a local dataset for these signs. By those reasons, we will generate one and validate if these algorithms are capable of doing this work with our dataset. So in general, we will generate a dataset with a traffic sign of Guadalajara, improve our dataset with image processing techniques and data augmentation, train deep learning algorithms to recognize the selected objects, and finally evaluate our results. Now, talking more specifically, we will first define the traffic signs to be detected and classified. Second, capture pictures of select traffic signs in Guadalajara. Then investigate image processing functions and algorithms that will enhance our dataset. Fourth, we will use image processing techniques to enhance our dataset. After that, post-processing capture image for deep learning. Then we will train the algorithm with this dataset and finally evaluate the network performance in ZMG. However, this project will have its limitation and it will be limited to run only on one computer, not a card, not a device, or anything like that. The system won't run in real time as well. It will only detect 8 different local traffic signs. Also, only one object detector results will be analyzed. It is not considered to detect traffic signs without daylight. Results will be analyzed with only pictures from Guadalajara area. Now, what are the challenges that we expect to face in traffic sign detection? Well, the first of them is that the signs may look similar between them. To give an example, speed limits may look really alike but are different on only one thing, the number. The second is the sign clearness. As they are items exposed outside, they may be faded or dirty, so their colors are no longer the same. Another problem is signal bending. Wind, accident, or other reason may bend a signal in a way that it cannot be detected as easy as it should. Fifth, visual pollution. A common thing to say in Guadalajara, where advertisement may block an object of interest or another object may look similar to it. And last, light conditions, we weather conditions, and finally, motion blur are other factors to consider. Currently, there are some other popular traffic sign dataset. In this slide, we can see on the left at the traffic sign detection benchmark from Germany. On the right, we find another image from the traffic sign from Belgium. And on the bottom, we find another one called Stereopolis, which was captured in France. As we can appreciate by this example, is that images were captured from a vehicle perspective by covering different tracks and using a color sensor camera. Also, most popular datasets were captured in European cities. On the other side, resolution and bounding both sides may vary between each different dataset. Same case happened for the class numbers. But what are the shortcomings on these datasets? First, images do not represent critical exposure to challenging environmental conditions. Also, they are not captured over control condition. They are all captured over control condition. Objects are limited to the region that were captured, and there is no public cross-location traffic sign dataset. And finally, and most important for a particular case, is that there is no public Mexican traffic sign dataset. Being said that, we came up with the following hypothesis. A computer vision algorithm trained with a dataset developed by your own will be able to detect and classify local traffic signs when running in one of our systems. We will evaluate this hypothesis by the following steps: image capture, image labeling, image augmentation, network training, and finally, network testing. For the first step, for image acquisition, we will have to decide which signal we will capture. We decided to choose at least one of every group from vertical traffic signs. From restrictive signs, we selected no parking and 60 km/h speed limit. From preventive signals, we choose pedestrian cross and 35 signal railroad cross. Now, for informative signals, we choose SIR, cruce de ferrocarril. For diverse signals, fotoinfracción. And finally, for preventive signal, we choose bus stop and bicycle cross. Being selected the objects to capture, we mark the tracks to be followed. Additionally, since railroad cross is a signal placed in certain particular locations of the city, we decided to visit those points to capture data and have a bigger sample on these signals. We started capturing data by driving to the city with an iPhone device, recording video horizontally on the top of the car. After these videos were captured, we tracked 1 out of 10 frames using an Unix 2 FFmpeg tool. With a collection of images being captured, we proceed with the next step, which was image labeling. For this step, we use Cartucho Open Labeling tool. It provides us a nice and simple interface for manually labeling data from different classes. The only thing to be careful while using this tool is to open a set of images smaller than 2000 samples. The tool can have some issues when you open big amount of image at the same time. This step was quite monotonous and time consuming, but at the end we finished with annotations in YOLO format as well as Pascal, with each annotation matching an image from the original image set with the same image name. At the end, we uploaded all this data into a Google Drive account for further processing, now in this new tool called Google Colab. With an original dataset being built, we proceed with the augmentation. We use CloudSat project for the data augmentation. The data that were originally uploaded is what we will call our original dataset. And by running CloudSat, we will generate our augmented dataset. This project was executed by running a set of scripts in Google Colab 2. We selected 15 different filters selected by the resemblance to TSD challenges. For example, we added some types of noises as well as salt and pepper. We added rotations, modified hue, saturation values, and so on. So we increased the amount of data that we process. One of the biggest challenges during this step was related to the time, since the processing time required to augmentate this data was greater than the time window provided at Google Colab. Our jobs were being killed by trying to perform this processing. We work around this issue by the creation of smaller batches. We created 32 different batches to be precise. Each of them contained a smaller section of the whole original dataset. Processing each batch at a time make the job to be divided into smaller tasks, and that way we can fit into the window. Finally, we list every image, split the data, and we created a train set and a test set from this augmented dataset. We use an 80-20% distribution to divide the augmented dataset into the test set and the train set. After the augmentation occurred, we post-process data to validate the correct behavior of the augmentation process. We made sure every image from the original dataset had their perspective annotation files and augmented images. Also, confirm that the image were in the correct formats that we expected and also that the files annotations were readable. Once that was done, we translated image from batches to two different folders, one folder for images and the other one for annotation. This helped YOLO framework to find them easy. Having everything set up, training was a simple part of the process. We modified the required configuration files, download everything needed for running YOLO, and enable Google Colab to work with the GPU. The problem was now that Google Colab did not map every file from the image and annotation folders. So once we tried to start our training process, it produced some failures due to missing images. To fix that, we set up a wait condition that was clear when every file in the training set was mapped. After that, the training process could begin. It was stopped only until we reached our desired mean average precision or when the Google Colab time window occurred. While this process was running, we were saving the network weights. This was done at different epochs, so when it was stopped, we could easily rerun again from a different checkpoint than the one we started before. Once this desired mean average precision is achieved, we use those weights to make the prediction. We serialize the process for passing every image in the test set through the network. While doing it, we stored every log for further analysis. In this point, we had a file with all the predictions made from the test set. Our next step was to evaluate the precision. It was done using mean average precision standard from Pascal BOC 2012 competition. The usage of Cartucho MAP or mean average precision tool was really useful. We downloaded every annotation file from the test set or from what now on we will call our ground truth along with the prediction results. We run the software and obtain the average precision for each class, as well as we calculated a mean value. Now everything has been explained. Let's talk about our results and how this process went. Our test set had more than 16,000 objects annotations captured from 35,000 different samples. Most of our label signs were number 8 and 7, Cruce de Ferrocarril and Vías del Tren 1, while the two with less annotation were Velocidad 60 km per hour and Autoinfracción Rojo Azul. We can see on the following pie chart the distribution across annotation and class. The same behavior occurred in the train set. It occurs as it was previously stated, this was only at 80-20 split from the whole augmented dataset. The difference is that in this set there were 143,000 images that contained 8,000 annotations. But as we can see, the distribution remains basically the same. Now, talking about the results obtained, we got a great precision in most categories. An impressive 82% on Vías del Tren and 179% on Cruce de Ferrocarril, with using an interception over union threshold of 0.0. It's important to state that the value that we use as our threshold was interception over union ratio. This helped us to know how accurate our predictions were in, in terms of the bounding bots. Now, when we passed from this interception over union from 0 to 25%, we can see that the values basically remain most likely the same. So the confidence level on the bounding bots used for this scenario, for these particular scenarios, are above this 25% ratio. But all of the classes remain in the same order, being the first and most accurate one Vías del Tren and the least less accurate Velocidad 60 km per hour with only a 24%. We can also highlight that the second not so great detected object was Autoinflación Rojo Azul with a small 32%. Now, as we continue to doing some experiments by moving the threshold to a higher level, we increase it to with a to a 50% and a 75%. As we can see, as we increase the threshold or average precision decrease. This is because as we increase our threshold, the harder it was for our detector to generate correct bounding bots, and so that's the reason why we had more false negative case for this particular scenario. This decreased a lot the highest precision. For example, Vías del Tren went from 82% to a small 54%. Also, the lowest value on average precision, went from Parada del Camión, which is now 2 2% accurate, which is not really not so great for this class that used to be at a high 36%. So that's for every particular class. But now let's compare against, in general, the mean average precision for all our data set. We can see we achieve a high 61% on when interception over union threshold was set up at 0, and as well really likely when it was set up to 25. We see it decrease when we increase the threshold, when, and it happened the same when we increase it to the maximum value or 0.75. On this point, the detector is actually not that reliable. So what do we learn from these experiments and from the development of this dataset? The first thing that we must state is that we should confirm our hypothesis that we were able to create this system that detected with a really nice precision the object that appear on each images. Also, comparing the number of classes across other high-resolution datasets, we find our dataset is allocated in the third position, behind LISA and Stereopolis. LISA catalogs 49 classes, 41 more than ours. while Stereopolis classifies 10 classes, just a couple more than ours. However, our dataset provides a much better resolution in terms of the space and image classes over image radio than these others. It also it also contains a better higher resolution. In terms of prediction cost, we can see that there is less impact on missing cruce de ferrocarril or vías del tren than other signals due to the high number of appearances in the dataset. Totally the opposite for peatón or prohibido estacionarse signals. In terms of mean average precision, the results obtained show that our best results occurred when interception over union was at its lowest value. As the threshold increased, the more inaccurate predictions appeared, representing false negative results. As another way to look at the results in terms of mean average precision for YOLO is that even though the bounding boxes may not be as accurate as they could be, the image classification occurs gracefully, granted an almost 70% in, in this matter. Talking about specific class results, we can confirm that in general, more the more an object appears in the dataset, the better the results obtained, confirmed with the two top categories, cruce de ferrocarril and vías del tren 1. This occurs with every interception over union threshold value. Another thing really important to remark is how good the results are on on these two top mentioned classes, uh, having around an 80% on both classes, something quite remarkable. Another thing to highlight is that while cruce de ferrocarril decreased around 50% their precision, when bounding bots threshold increased to 75%, via del tren suffered less. Both shapes are different, being the first an X and the other one a rhombus. Their color is quite different too, being the first white, white and black with letters, and the second one being yellow with block drawing. So we can see that some classes will learn better than other classes. While using a threshold value of 0 to 20 and 50, the lowest classes remain the same, but tables turned when 75 interception over union criteria was used. From being, from being velocidad 60 km per hour and autoinfracción, rojo-azul, in previous cases, to now parada de camión en bicicleta azul-amarilla in the last case. This means that most of the predictions using YOLO present an interception over union between 50 and 75%. Also, it implies that while other class lack of precision at detection, they get better bounding bots than these last two. The last thing that we want to state is that cloud also has its trade-offs. It helps us a lot by providing the capability to work with a GPU and to work everywhere, as in every location from a different device. It also has a disadvantage as the capacity that could be allocated in terms of memory is limited by the account subscribed by the user account that is using the service. The second and most important thing, or the biggest trade-off on using Google Colab, is the time window capacity. We are limited to work for at most 12 hours, and once you're hitting that limit constantly, you're being turned down from Google Colab services. For temporary, it's not something on the long term, but it's something to have in consideration when working with this kind of projects, that every task must be divided into smaller tasks, and you must consider saving some checkpoints in order to stop the process and rerun again. So being said that, what is next? Well, the first step would be to publish your data. As of now, it is only available in a local device, and if anyone is interested in exploring this dataset, it would be ideal for them to just simply download it from either a GitHub or a shared drive repository. The second thing would be to increase our catalog, since as of now we are only considering 8 different traffic signs. There are hundreds of traffic signs in Mexico, and we could explore these other options. Also, another thing that can be considered is capturing data in other weather and seasons. Also, another thing that was not explored is expanding the area where the pictures were taken. For this particular experiment, we decided to choose Guadalajara, but it would be quite interesting if we decided to start capturing images from Sinaloa, from Ciudad de Mexico, from Nuevo León, for example, to mention other places. Also, fine-tuning will be something worth experimenting with, since as of now, for this experiment, we only took YOLO as it was. We did not modify anything in configuration or else. If we fine-tune this algorithm, could we get better results than the ones that we did? Or where's the top with this algorithm and this dataset? Also, exploring new algorithms is quite interesting as well. There are hundreds of new deep learning algorithms for object detection and classification. As in this project, we use only YOLO, but what about taking other algorithms in consideration? And finally, our current dataset is labeled for object detection and classification for YOLO and Pascal. However, there are other datasets that have most a bigger amount of annotations for other purposes, for example, label for segmentations. So here are the results from my thesis, and these were the next steps that I consider that will improve the relevance and scope of this project. I hope that you like it, and in case you have any questions, please let me know in the comment section. Thank you very much and hope you have a nice day.